Hi, good morning, everyone. Thank you for coming for our first UTIG Friday seminar of the fall season, the first one. And this seminar, this fall seminar will be slightly different, as we got, as you've seen from Shoshu's email, a lot of new recruitment, postdoc recruitment that coming from various new kind of expertise bringing into UTIG, from a marine geodesy to seismic of planetary moons. So we will have some diversity between postdocs and outsider guests. So I'm very happy that our first guest is our own Alice Sherman. She joined a few months ago. She will tell you about her work she's doing for both industry and academia. And this is in a perfect timing because we also have our guests from EMGS here, Frederick and Doug from Norway, which pretty much the gold standard of marine CSEM. So I'm very happy to host them, and they will give a talk later at 1 o'clock at the second floor seminar. So for those of you who haven't met Dallas yet, Dallas graduated her undergrad at the UC San Diego. That's correct. 2012 in environmental engineering. Then she continued to a PhD doing geophysics, specializing in marine electromagnetic methods with Steve Constable at Scripps EMLab, where she followed by being staff research assistant, and then she moved around 2019 to a company called Frontier in Canada that does a lot of mineral exploration all over the world, Greenland, and she will show you some of the bits of her diversity of the stuff she does. And when I got the position here, I convinced Dallas with the light force to come back to academia. So I'm honored to have her back into academia, and please enjoy her talk.
Thank you for that intro, Eric. I think my microphone might be too close to my face. Okay. Yeah, so I'm happy to be back here. Happy to have all of you here. Thanks so much for coming this morning. Right now, I am a postdoc in Eric's lab, the Ocean and Earth Electromagnetics laboratory. So today, I want to give you an idea of kind of who I am and what my background is, as well as focus on the role of geophysics and specifically marine electromagnetics in developing resources and assessing hazards that are going to be important for developing a sustainable future. That button didn't do what I wanted it to. There we go. Okay. So I'm going to start by just stating some of the big global challenges that geophysics have an important role to play in. The first is volcanic hazards, which I won't be touching on today, but it is an excellent choice for the application of electromagnetic methods. The water crisis, we're looking at water shortages that could affect over half the world by 2050. And also the increasing need for minerals. We're looking at increasing demand there. It's estimated that demand will double by 2050. So this is kind of all under the umbrella of humanitarian geophysics, which covers everything from geohazards to climate change issues, the need for more freshwater resources, and the transition from hydrocarbon to renewable energy sources. I'm going to be focusing on these last three for this talk. In particular, from my consulting days, it became obvious that as the clean energy transition kind of gains momentum, it's the demand for those rare earth minerals are driving industry into more remote regions and places that have deposits but are just very logistically difficult to access. And so we're seeing more and more of that kind of exploration. And so the geophysics I did in consulting was not only focused on quantifying the ore body in exploration, but also in guiding infrastructure development in those places. So I'm going to cover quite a bit of ground today. I'm going to show you a couple examples from consulting days regarding infrastructure development and exploration, and then 2 more in-depth marine electromagnetic case studies, one focused on fresh groundwater aquifers offshore Hawaii, and the other about relic subsea permafrost on the north coast of Alaska and its associated greenhouse gases that could be released in the near future. So the company I worked for, Frontier, we did do some mineral exploration, but a lot of our work was focused on small scale, high resolution geophysics for engineering and geotechnical purposes. So in this particular example, we're in remote northern BC. This is a future LNG processing plant and port infrastructure area. So our task was to determine sediment thickness in the potential port location. This is a very deep fjord. I think it drops off quite steeply down to 300-400 meters depth. So it's a good place for large ships to get in there, which I think is why they're locating it in this remote spot. So to do this, we still don't have a mouse. So to do this, we used a seismic boomer system, which you can see in the left-hand photo there. The boomer system is basically just 2 large metal plates that are banging together. It produces a lower frequency than the sparker system. So we were able to collect high resolution, high quality data out to like 400 milliseconds. I have an example section here. So there is a clear kind of sediment basin on the left-hand side, and then a good amount of the seafloor is actually just exposed bedrock. Second example that's related to infrastructure is actually a highway expansion project through a mountain pass, also in British Columbia. So again, left photo, you can see the highway they're looking to expand. So they kind of have 2 choices. They're going to do a combination of building like bridge structures out onto the steep slope and blasting their way inward. So they were looking for depth to bedrock information, and also if there was any faulting in the region, they should be wary of. So we were doing a seismic refraction survey. A couple example results are shown on the right-hand side. We use the method of differences for that interpretation instead of tomography. So we do get a discrete overburden to bedrock transition. And we did identify a few low velocity zones within the bedrock layer, which does suggest some amount of localized shearing or deformation. And the logistics of this project were also challenging. We did end up working with a rope access team so that we could safely access these steep sides of the highway. And then we were also working with traffic control and the railway safety people because often the railway was on our side of the river and we were using explosives as the source. So we had to do a lot of communication to keep the public and the railway safe for this one. Okay, and my last quick little example from consulting is more regarding mineral exploration in support of renewable energy. This particular deposit is in Greenland, and it's a molybdenum deposit, which is used in making steel alloys, make steel harder, more resistant to wear, more electrically conductive. And it's important in building things like engines and also in building like windmill components on the renewable energy front. So the original plan sorry, I don't know why my mouse will not show up on the display window here. So it won't help the people online, will it? But I can point here. What? I do have a mouse. Oh, that's this mouse, which does that annoying thing every time I move it. That's not my mouse. I'll just point for people in the room. Okay, so this is a plan map of the survey area. The deposit is actually down over here. And then the port where they need to get all of that ore to is all the way over here. So they've got 3 plus a smaller 4th glacier over there they need to get across in order to get any of that ore out. So their original plan was to build a tunnel under those glaciers. And so one of our tasks was to use ice radar just to measure the ice thickness. And unfortunately for them, we did determine that right around here, where this glacier gets thicker, their planned tunnel, all of their planned tunnels would actually come out into the glacial ice at that location. So we sent them back to the drawing board on that one, but better to know now than when you're drilling your tunnel. This was, I'm not used to having not fully public data, so I'm like, how much am I allowed to say? It's East Greenland, Southeast Greenland. I think I can say that much. Okay, so now as promised, after that overview, we're going to dive a bit deeper into marine electromagnetic methods specifically. So we're going to start off with a bit of theory, talk about instruments, and then I'll get into the 2 case studies. So electromagnetic methods are sensitive to bulk resistivity. So that's a combination of the resistivity of the rock matrix and any pore fluids that are present. So it's going to be sensitive to the porosity of the rock, the amount of melt, any volatiles and the ions present within those pore fluids. It comes in kind of 2 different flavors. The first is passive magnetotellurics, which is kind of drawn on the right-hand side. And this just involves nodal receivers that are passively recording the magnetic field and electric field. And it's relying on natural variations in the Earth's magnetic field to be the source. And MT is routinely used terrestrially and in the marine environment. The other half is this active source, AEM, this controlled source electromagnetics, which requires a man-made source. In the marine environment, what we're typically using is an electric dipole transmitter. So in this example, it's a deep-towed transmitter. It has an antenna that's a couple 100 meters long, and it's transmitting a couple 100 amps on that dipole. So resistivity, the bulk resistivity, which is what we're measuring or what we're sensitive to, is an inherent property of Earth materials, and it has a very broad range. So this is why most of our models are plotted on a logarithmic scale. And EM methods are pretty much a good candidate whenever you have a resistivity contrast. So for something like volcanic hazards, where you might be interested in looking at the magma chamber and kind of the plumbing of how that comes to surface, you'd be looking at some kind of melt, which is quite conductive, against a host background of colder solid rock that would be resistive. So that's a good resistivity contrast that you can target with EM. The examples I'll give you today are focus more on this bottom layer of this chart, where we're looking at freshwater and or permafrost, which are going to be really resistive targets against a host background of marine sediments that are saturated with seawater and barely conductive. So the active and the passive, the CSEM and the MT, are based on related physics. MT is an induction method. So it's pretty much described by Faraday's law, which is just saying that a time-varying magnetic field induces current flow in media. So in the case of MT, that time-varying magnetic field is going to come from solar activity and solar wind hitting the magnetosphere and causing changes to the Earth's magnetic field. And then we're measuring the induced electric field from those time variations. For the active CSEM component, It's described by Ampere's law, which is describing the shape of the magnetic field that's generated by current flowing in a bar or in a piece of wire. So for CECM, the source, the JS, is that electric dipole I talked about earlier. And then the electric field of that dipole is drives current flow in conductive bodies, which produces secondary magnetic and secondary electric fields. So what we're actually measuring on the surface is a combination of the primary and secondary fields. And then this should just play automatically. This is a nice movie that Carrie Key made, just kind of showing how those waves propagate through the subsurface. You may have noticed that we aren't actually measuring the magnetic field when we do CECM surveys. We are only measuring the electric field. So before we can actually use these equations, we have to decouple them and get an equation that's expressed exclusively in the electric field terms. So that involves taking the curl of both of these and doing some substitution. The net result is you get the wave equation for EM, and for the low frequency EM that we use, that simplifies to the diffusion equation. Okay, so the basic workflow for CECM data, how we get from fieldwork to a model of subsurface resistivity, is that we transmit some kind of square wave. This is our favorite. We record the electric field and get something that looks similar to that square wave at the receivers. We do a Fourier transform of that time series data and stack it usually into 1-minute intervals. And we display those complex numbers as amplitude and phase. And then we're using that amplitude and phase in our inversion code to produce the resistivity models. We are typically using Carrie Key's MariTT-EM code. It's a finite element code, and it uses the OCEEM inversion method. So it's going to give us smooth models of the subsurface. So it's very good at weeding out artifacts that aren't strictly required for the data, but it is going to produce smooth sections. Okay, so that's all the theory I'm going to go through. I'm going to talk a little bit about instruments. So there has been a kind of continuous development of instruments that started with MT and nodal CECM, which is quite good for deeper studies. And then we transitioned, added this deep-towed fixed offset receiver option. So this does not require anything to be on the seafloor, so it dramatically increases efficiency of data collection, and you have shorter source receiver offsets, and so it's going to increase the resolution. But in exchange, you're not sensitive to the same depth as the nodal or MT systems. And then lastly, in order to access shallow coastal waters, we took this deep-towed system and designed it so that it would float on the surface. So we could access very shallow coastal waters to study things like the subsea permafrost. So a lot of this development in academia has been led by the Scripps Marine EM lab. Other academic institutions that have CM sources are GeoMar and Southampton, and more recently, the Hawaii Institute of Geophysics and Planetology and the OCEEMlab at UTIG have created a joint CECM instrument facility, which I'll talk briefly about at the end. So today, both of my case studies are using this surface towed system. So we have a transmitter on the boat, antennas in the water. The dipole is about 100 meters, and we're transmitting somewhere between 50 and 100 amps. And then we're using up to 4 receivers from 250 meters behind the source to 1 kilometer behind the source. And then just an overview of some applications that, from my personal history, that these different kinds of instruments have been used on. The bottom 2 are what I'm going to talk about today. And the one I'm most excited about is actually the paper that just came out in Nature about the Hikurangi subduction zone. That was a combination of MT and deep-towed CACM. I was involved in the field work, but haven't seen the results yet. So that was exciting news. Okay, actually on to case studies. So the first one is offshore Hawaii. It's the IQY project, which is a big NSF-funded program to look at the Hualalai. Did I pronounce that correctly? Hualalai terrestrial aquifer system on the Big Island of Hawaii. And so the Hualalai aquifer system is highlighted here. They track rainfall and recharge pumping out of the aquifer. And some isotope studies suggest that there is a 40% mismatch between the recharge and the discharge that they're measuring. So the obvious question is, where are those waters going? And can we answer that question with some marine CACM? So this is the conventional model that was being used at the time, where there is kind of one freshwater aquifer has saltwater intrusion happening from like all other sides. And the only place that there is freshwater discharge is along the coast at that submarine discharge area. So we're guessing that that's not the only way that freshwater gets to the ocean. So we did a CACM survey to figure out if we could identify where these other losses were coming from. So this was work done in 2018 with Eric, and we collected data all along the West Coast here, pretty much parallel to the entire Hualalai aquifer system. And spent about 8 days out in the field, collected 22 straight line profiles and did all the inverting with MARI 2D EM. So we have a series of 2D models that we are going to take a look at. So this is a fence plot of all of the 2D inversions. The two main things to take away from this plot are that it looks like offshore Kona. There is a large scale freshwater reservoir. That's that big blue section offshore Kona. The color scale we're looking at here, red is going to indicate very conductive saline sediments, and deep blue is going to be very freshwater. Anything in between is going to be some level of freshened brine. So there's that large scale reservoir offshore Kona, and then a lot of smaller freshened sections across all of these other inversions. So we're going to take a closer look at this line 3 up in the north. And so what we're actually seeing in these inversions is a layered effect. So we're seeing the top layer is conductive marine sediments, kind of what we would expect. And then it transitions into the more resistive freshwater saturated layer. And then the unusual part is that it goes back to a marine sediment conductivity, and then the last layer is again that more resistive freshened layer. So on this slide, we have the model results and residuals and some information about the inversion. So this was only using the first 3 corpuses. We thought the fourth was just too noisy. 2 frequencies and reasonably high error floors in order to get down to that RMS misfit of 1. And so this structure led to a new conceptual model of the aquifer. I think this is a nice little movie that I'll play possibly. There we go. So we still have the rain recharging the terrestrial system. It percolates through the porous basalts into that terrestrial aquifer. And then instead of just coming out at the coast, it's going to travel through the porous basalts, but constrained by these low permeability ash and clay layers. And so it's going to flow all the way out, possibly all the way out to the flank where the seafloor drops off on this steep slope. And so this is a new mechanism for freshwater transport that is not going to be measured by the coastal submarine groundwater discharge only. So that is our marine CSM answer to where is that 40% of fresh water going. And yeah, I didn't end up including these slides for time purposes, but we also managed to image some freshwater plumes as well that suggest not only is the discharge is coming from the coast, possibly all the way out onto these flanks, and also in between in these freshwater plumes that are coming up. Okay, so the last thing is moving on from freshwater and into a more climate change related topic. So the surface-towed marine CCM system was originally designed to map the subsea permafrost on the North Shore of Alaska. Well, I guess I'll just start talking about permafrost, and why we're interested will become clear. So permafrost underlies about 20% of land in the Northern Hemisphere, which is the dark blue parts on this map. It forms when the ground is exposed to sub-freezing temperatures for an extended period of time, technically defined as ground that's been below freezing for over 2 years. In the last 20,000 years, sea level has risen between 100 and 120 meters. And so these low-lying coastal regions in the Arctic, which are highlighted in this map in blue, light blue, those low-lying coastal regions that had permafrost formed during the last glacial maximum have been submerged over the last 20,000 years. And so all of this subsea permafrost is kind of a relic of that time, and it is now climatically unstable. It's in a state of degradation because it's been exposed to that warm saline boundary condition of the ocean water. So that's why, even though the subsea permafrost is a small percentage of the global permafrost, it is the most climatically unstable, which is why we're interested in studying it. And then one important note is that geophysical methods are typically not, they're not sensitive to temperature, they're sensitive to other bulk properties. So the permafrost we are sensitive to is actually ice-bearing permafrost. As you can imagine, if you have a water-saturated sediment that is below freezing for many years, ice crystals will start to form in those pore spaces. And so it's the replacement of liquid water with ice crystals that increases the resistivity and the seismic velocity of the permafrost. And so that is, the ice content is actually what we're sensitive to. So permafrost has two potential carbon reservoirs that could be released as it thaws. The first is an ancient organic carbon reservoir. Even though the technical definition of permafrost is only 2 years below freezing, it takes thousands of years to form permafrost that's hundreds of meters thick to reach the 600-meter thick permafrost that's seen on shore in Alaska. That would take about 20,000 years to form. So there is this reservoir of ancient carbon that, as the permafrost thaws and microbial activity resumes, will be consumed and released as CO2 or methane, both of which are potent greenhouse gases that could have significant impacts on the changing climate and our climate predictions. The second reservoir is associated gas hydrates. So gas hydrates are when gases, typically methane, get trapped in ice crystals. And so they're stable at low temperatures and high pressures. So in the schematic on the right there, you can see that they're typically in the shallow seafloor below about 500 meters water depth. But the cold temperatures of the permafrost actually allow that gas hydrate stability zone to extend to onshore and into shallow waters. And so as the permafrost warms, those gas hydrates are going to dissociate and release the trapped methane gases. And because this is in shallow water, that vented methane is quite likely to reach the atmosphere before getting absorbed into the water column. And so it's a potential big source of another potent greenhouse gas. So historically, there have been two ways that the extent of the subsea permafrost has been quantified. The first is boreholes. The right-hand image is one example of some property logs from the borehole. It's like they have the caliper, the self potential, gamma radiation, and then resistivity and seismic velocity are the final two. Pink highlights high saturation ice-bearing permafrost, and yellow highlights intermediate saturation ice-bearing permafrost. And so you can see that the resistivity and seismic velocity are the two best indicators of those saturation regions. There have been active seismic surveys in the area, an example of which is this left-hand figure. In the middle panel, you can see the permafrost layer revection. They're getting velocities around 3,900 meters per second. The trouble we can run into with seismic is that it's quite sensitive to the top of the permafrost. You'll get a solid refraction or reflection off the increase in velocity, and you won't get any, or you won't get a strong or you won't get any response from the base of permafrost, both because it's likely it's a more diffuse boundary, and also because you have that velocity inversion that seismic does not respond well to. Right, so drill holes, you can get a lot of detailed information, but it's only at one location and they're quite expensive. Seismic, as I said, you're getting information about the depth to the top of the permafrost. With a CECM survey, we're hoping to add information about the depth to the base of the ice-bearing permafrost, and then get some more details about the ice saturation using our resistivity values. So this survey location was the North Shore of Alaska. We were based out of Prudhoe Bay. The top figure is a kind of summary figure from the Brothers et al. Paper about the active seismic survey they conducted. The big yellow line out along the coast is the 100 or 120 meter isobath. So that's where, prior to these surveys, that's where it was assumed the subsea permafrost extended to, just because that's how much sea level has risen since the last glacial maximum. And the thick red line more or less ends up following the 20 meter isobath. And that's the edge of ice-bearing permafrost that seismic data detected. So already we're seeing quite a discrepancy between how much we assumed was there and how much there actually appears to be offshore. So we collected marine CECM data along the lines shown in the bottom figure. We were there 2 separate years, about a week each. And unfortunately, both times we were there, the sea ice it never went further out than about the 20 meter isobath. So we were stuck pretty close to shore, which is why we tried to spread our coverage from, east of Prudhoe Bay all the way to Harrison Bay. It's about 200 kilometers of coastline, but we were not able to get long shore perpendicular profiles. So we weren't able to map the transition from high saturation ice-bearing permafrost to maybe like discontinuous to normal permafrost offshore we have only been able to quantify the extent kind of near shore. Okay, so I am going to show you inversion results from two separate lines, which I have labeled in this figure, and also a borehole for comparison, which is labeled at the bottom as well. So the first inversion is this shore perpendicular toe. You can see at the end there where we kind of went offline because we were trying to avoid the sea ice. It's just very hard to dodge sea ice when you have a whole kilometer of stuff behind your boat. You don't dodge well. Yeah, so this is an isotropic inversion. Starting model was a 1 ohmmeter half space. Has a 3% noise floor, but only converged to an RMS of 1.5. So as expected, the permafrost does thin as you move offshore. Shore is kind of where zero is, and the line extends almost 8 kilometers offshore. And as it thins offshore, it thins mostly from the bottom up, indicating the thermal forces from the geothermal gradient thawing the permafrost from the bottom may work faster, be a stronger driving force than the saline intrusion or conductive forces from the ocean. And then past, 6.5 kilometers, the permafrost appears to start to become a bit discontinuous. But like I said, unfortunately, we couldn't get farther offshore to actually see the end of the ice-bearing sections. So the other important thing to know about this inversion is that it is amplitude only. We had a timing issue when we collected this data, and so we don't have any good phase data. The only data we have is amplitude. And with the amplitude only, we were able to fit the data with an isotropic model. Once we fixed the timing problem and got good phase data, we were not able to fit the phase data with an isotropic medium. So we allowed for transverse anisotropy. So anisotropy is just the directional dependence of the electrical resistivity. The anisotropy we're dealing with in this case is likely due to fine layering below the resolution of the CSEM method. And so you can think of the vertical resistivity as adding up these layers in series. And so the overall resistivity you see with the vertical resistivity is going to be closer to the most resistive layers. And then the horizontal resistivity is like adding those layers up in parallel. And so you're going to be more sensitive to the more conductive layers. And so this is a shore parallel tow that does include good phase data. And it is an anisotropic inversion. So in the top panel, we have horizontal resistivity, which, as expected, is more sensitive to the conductive layers, which appear to just be marine sediment. This is a similar color scale to Hawaii. So the reds are still going to be marine sediment, saltwater saturated sediment, and the dark blue is going to be more indicative of ice-bearing sediment. And then, of course, the second panel is the vertical resistivity, and that's where we start seeing indications of these resistive areas that are likely ice-bearing. And then the third panel is the anisotropy ratio. So that's the vertical divided by the horizontal resistivity. And the anisotropy ratio actually gives a better definition to the base of that resistive layer than just the vertical resistivity does. And the fact that we are requiring anisotropy suggests that the ice-bearing sediments may have this fine layering, but the freshened groundwater probably wouldn't. And so not on this line, but in some other areas, there are resistive sections that are not as anisotropic. And so we interpret those as probably just areas of fresh and groundwater and not necessarily ice bearing. So we do use the anisotropy as a check on whether or not the resistivity is actually indicative of ice bearing sediments. And we can double check our work a bit because we do have resistivity logs from the drill holes. And so what I've done here is taken the resistivity log and then added up those layers in parallel and then averaged them with a 50-meter smoothing window to kind of mimic the resolution of the marine CCM survey. And that calculation gives me the horizontal resistivity, which is plotted in the dashed blue line. And then doing the same thing, adding up those layers in series to get the vertical resistivity average, which is plotted in the red line on the first panel. And so we do see more of a discrepancy between those two through the region of high ice saturation. And then the second panel is the anisotropy ratio. And again, we see an increased, up to 10 to 20 anisotropy ratio in those ice saturated areas, which is consistent with our inversions. And that the sharp increase and then fall off of that anisotropy ratio is also a good indication of the top and bottom of that section. And then the last thing I've done in this is use the resistivity and a reformation of Archie's law to calculate the ice saturation. So Archie's law is a very old empirical calculation to get saturation levels out of a porous media. So it's not the best, but it's handy. So I'm using empirical values from previously published papers related to the area. And with this formulation, we're seeing ice saturations of over 90% in the high saturation areas and closer to 50% ice saturation levels in the kind of intermediate ice bearing regions. And so we can apply that same formulation to our inversions, and kind of as expected in those higher deep blue areas, we're seeing over 80% and more background levels of that closer to 50% intermediate kind of ice bearing. Okay, so the last thing we did was we inverted over 20 separate lines, and then we combined them to create plan maps of the depth to top of the ice bearing permafrost, and then the thickness isopack of that permafrost. Couple things to note. The first is when we're looking at the top figure, which is the depth to the top of the permafrost. The shallowest, I tried to keep its color scales consistent with blue indicates more permafrost in some ways. So in the top, blue is going to be shallower, and in the bottom, blue is going to be thicker. So in the top one, the bluest and therefore the shallowest section is actually directly offshore the Sagamore River. And so we suspect that there is an associated fresh groundwater output there as well. And as you freshen the pore fluids, the freezing point of the pore fluids is actually going to increase. And so freshening of the pore fluids could actually cause them to refreeze in under their current thermal conditions. And so we're thinking that that is actually a preserving effect on this shallow permafrost. And then over on the left-hand side, where in the top you see some orangish, fairly deep to the top of permafrost lines, that's offshore the Colville River. This is in Harrison Bay. And there is actually one other line that's like right here. That doesn't show up on either of these maps because the whole inversion was below 10 ohm meters. So there wasn't any permafrost to be detected on that line. So this area in Harrison Bay is italic. It's a region of unfrozen ground in the midst of otherwise pretty continuous permafrost. And those often form under the beds of large rivers. And so this could be like a paleo river channel or something like that. So with all this information, once we have the depth to the base of the permafrost, we can use that to calculate the new extent of the gas hydrate stability zone and get a better kind of maximum estimate of how much methane there is here to be potentially released. And this is also just a really good baseline measurement. This data was collected in 2018. So if we go back, in a decade or something, we'll be able to track how quickly the degradation is happening because both the EM and the seismic suggest that there is actually less subsea permafrost than we had originally assumed. The question still remains that, was there less that was submerged and that's why there's less, or is it just thawing much more rapidly than we originally thought? And so those are kind of the future questions that we can continue to work toward. Okay. Real quick, I'm gonna blow through some future plans. We have some instrument development plans and some more freshwater related research plans. The first thing of note is that the lab has acquired the old PGS EM streamer system, which is a huge EM streamer. At the moment, it's too big to use on a UNOLS vessel. It was originally designed to work in conjunction with a seismic streamer so that industry could collect both data sets at the same time. Due to arrive here September 6th, we're going to do some refurbishment and pare it down to be more academic friendly so it can be used on UNOLS vessel. We're also going to add a suite of USBL systems so that we can dramatically improve navigation of our instruments, and also add an in-house designed fresh sense system, which will measure the conductivity of the water column at the same depth as the sensors, among other things. But the combination of knowing that water conductivity and improved navigation will let us have much increased accuracy and lower noise in our data so that we can resolve smaller details in our models. And so this will be one of the things that's part of the UTIG Hawaii Joint Marine CCM facility. And the other instrument that is part of that comes from Amir, who is moving from GMR to Hawaii. And it's his surface towed system. It's a SWAN system. The biggest advantage it has over the instruments we used in Hawaii and the Arctic is that it can actually be submerged a few meters, which gives you a lot more flexibility in terms of boat traffic. You have to worry less about all the small fishing boats and things running over your cables, which is a really big deal, I promise. So this is one proposal that we're submitting quite soon, looking at characterizing the fresh saltwater interface of submarine aquifers, and that's on the East Coast. So this is an ideal place to use that SWAN system because the bathymetry is fairly shallow. And we're also going to be using UTIG Sparker system. So we're going to get a really comprehensive data set that involves both seismic and EM, which are complementary data sets to each other. So I'm very excited about this. And lastly, doing basically the experiment we did in Hawaii, but offshore Israel. And the kind of black and gray image on the top right there shows the bathymetry of the canyon we're interested in. And you can see the bathymetry drops off to over 500 meters water depth. So this is going to be a perfect place to combine using the refurbished PGS streamer system and the SWAN system for shallower bathymetries. So that's what we're getting up to in the near future. And ready for questions.
Thank you, Dallas, for this great talk. I just want to, before I move into question, just open a bracket with a slightly note. So what you've seen here, this is, there is a wide conception in academia that because of the physics of EM, it's a low resolution method. And you can see also because our academic instruments are not as developed as industry and our coding not as developed, we still have, you've seen from, for the range of our error floors, ranges between 3 to 7. And we're struggling with the RMS misfit, but we can do better than that. And one of my prime goal in our lab, me and Dallas, is to get to industry standards so we can understand better and high resolution. And if you come to the talk by EMGS, they're already there. Their resolution is comparable to seismic resolution. So, well, almost, if you, well, they have to be integrated. But the idea is that we're going towards the age that like we will couple seismic and EM together, and then that will give us more closely to the better kind of description of Earth. Sorry for that long brackets. Now I question. John.
Thanks, Alice. That was a great talk. I was just curious in your permafrost, there was one zone that had super shallow permafrost. Do you have any insight into what was causing that zone there?
Yeah, our thought. Way farther back. Yeah, this area right here.
Yep, that's it.
Yeah. Yeah. So our thought there was groundwater discharge associated with a river there, freshening the pore fluids because the ocean is about -1 degree up there. So that's salt water will be liquid there. So the more saline pore fluids would be liquid, but if they're freshened to the point that -1 is below I always get the directions backwards, below the freezing point, then as they're freshened, they could actually refreeze under those thermal conditions. So yeah, that was our thought for that area.
Thanks.
While you're on this slide, can you just explain what the colored circles are?
Oh yeah. So the colored circles are the boreholes in the area. They're colored under the same color scale. Except for, I don't know why I did this. The outline is in like pink, so they almost don't look like they're on the same color scale. So the major discrepancies are these two boreholes that are showing permafrost pretty much at surface. And that's going to be because those boreholes are actually on islands. And so they are actually still exposed to the sub-freezing Arctic winters. And so it's not surprising that they have permafrost shallow there. Yeah.
Oh, thank you. I have a dumb question as well. When you're doing all of these surveys, if you have like a thunderstorm, does that mess everything up? Because of like the lightning?
Yeah. As a general rule, we don't do much operating in thunderstorms for safety.
Less safe.
I mean, but yeah, lightning is actually one of the is one of the sources for like magnetotelluric methods. It does have large scale induction effects. Yeah.
So we like solar winds because it gives us good data.
Okay. Thanks for this really interesting talk, Dallas. It was really, really nice to see all your applications that are very different to our oil and gas applications. I guess that's part of our reason to be here, to learn a little bit more what's happening here. I got really intrigued by the resistivity log that you were showing through the permafrost, and maybe you mentioned it and I wasn't paying attention, because I think it's really interesting to see how much the resistivity is fluctuating from 10 ohm meters to 1000 ohm meters. And I was wondering what the interpretation of that is. Is it that, you know, there's a section that is really frozen and then it's less frozen and then it's frozen again? So I was wondering whether you could comment a little bit on that.
So, okay, I'll start with my caveat that I'm not actually familiar with the instrument they used or anything like that. So yeah, when I first looked at these, I was almost like, well, that instrument is really noisy, right? But there are a lot more of these variations in that high saturation area. So there is some combination of probably instrument noise and something real going on. But so yeah, our thought for that was just that as ice forms, it extrudes like any ions, right? So it's actually pure water. And so you're going to end up with, you know, if most of your pore fluid becomes ice, you're going to end up with kind of like a hypersaline or super ionic fluid. And so if there are any, fine layers in the sediments, they might kind of separate. So that was our thought to explain that. You're going to have, regions of like pure ice and then regions of that extruded ions. That's going to be,
Yeah, thanks for the talk. Just a comment to that. I also think that's a lithology effect you're looking at there, because it's similar to what we see in gas hydrous, is that they really resistive where you have sand, but they're not resistive in shell. And this is just a smaller scale of that. That's my thought on that.
Yeah.
Any one last question that we have time for? Or if not, yeah,
I still
sure.
have one
Fredrik.
question. So on the Hawaii survey, so
Yeah.
look like that some of the survey lines were bent or curved.
Mm.
Is that something you can invert with Mari 2DM? Or did you how did you handle this?
Yeah, so I believe we kind of broke those towed lines into like straight line segments. Yeah. So Mari 2D does have like it does have an offline component, and it can account for, maybe a couple 100 meters offline. But yeah, so those were broken up.
But more interesting, just to refine on that, if you go east and east, so you can do 500 offside, but then if you go east and then west, the inversion breaks. So this is how I kind of discretize the lines, and then so that means a lot of more work because each one of them has to be inverted separately. Well, I think we're gonna wrap it up. So let's thank Dallas again for this great talk.